Welcome back, Focus Learners. Today we're tackling an absolute superpower in the DIY electronics world, taking wild, unpredictable power and taming it into something perfectly precise. But before we break down the circuit we've got queued up today, I have a very important question for you, and I want to make sure I ask it right.
आप इस एक्सप्लेनर को किस भाषा में देखना पसंद करेंगे? हम इसे उसी भाषा में बनाएंगे.
Which language would you prefer to watch this explainer in? We'll make it in that exact language for you.
¿En qué idioma preferirías ver esta explicación?
La haremos en ese idioma.
Dans quelle langue préféreriez-vous regarder cette explication? Nous la ferons dans cette langue.
In welcher Sprache würdest du diese Erklärung am liebsten sehen? Wir werden sie in dieser Sprache erstellen. Drop your preference in the comments. But, for today's breakdown, we're just going to stick to simple, clear English. Okay, let's dive into this.
If you've ever dabbled in DIY electronics, you know the struggle, right? Managing power is pretty much hurdle number one. You might have this massive, beefy power supply, but your delicate little LED or that custom microcontroller you just bought, it only needs a fraction of that juice. Give it too much, it literally fries. Give it too little, it doesn't even turn on. Think of this complete LM317 variable DC voltage regulator circuit as an incredibly helpful black box. Raw, chaotic energy goes in the top, and smooth, perfectly dialed-in energy comes out the bottom. Our goal today is to pry open this black box and figure out exactly how these individual pieces work together to completely solve our power problem. So, to really get what's going on, we have to look at the big picture first. Check out the top and the bottom of the diagram. Up at the top, we've got our input DC, and that ranges from 3 volts all the way up to 40 volts. This is that raw, fluctuating power we talked about, maybe from a wall adapter, a battery pack, or even a solar panel. Now look down at the bottom. That's our output DC. Notice how those numbers have completely tightened up? We're looking at 1.25 volts to 37 volts. This entire circuit has one job. Take whatever crazy voltage you feed into the top and step it down to a rock-solid, controllable output at the bottom. Actually, scratch that. Before we get into the weeds with the specific components, I gotta point out that top input number again, 40 volts. That is seriously high for a beginner-friendly setup, and it highlights just how incredibly robust this circuit is. It means you can hook this thing up to a standard 9-volt battery, a 12-volt car battery, or even a hefty 36-volt power supply, and it won't even break a sweat. It gives you a massive, safe buffer to play around with, without constantly worrying about accidentally destroying your board. Okay, let's meet the star of the show. Up there in the top right, that's the LM317. This little piece of hardware with the 3 silver legs and the metal hat is the actual regulator, doing all the heavy lifting. I like to think of the LM317 as a highly disciplined bouncer at a club, or maybe a heavy-duty water valve. No matter how much electrical pressure is pushing against it from the top input, this chip physically restricts the flow. It only lets a very specific, much lower amount of voltage pass through its terminals and into the rest of the circuit. But, a star is absolutely nothing without its supporting cast. The LM317T just cannot do this job alone. It needs instructions, it needs stability, and it definitely needs protection. So we've got the Pot5K, the R220 resistor, a 470 microfarad 50-volt capacitor, and a couple of IN 4.07 diodes. By chunking it down like this, the whole thing instantly feels way less overwhelming, right? Let's see exactly how this crew helps our bouncer out. Now, what's really interesting about this setup is the dynamic between the LM317T on the right and the Pot5K sitting right next to it on the left. Pot is just short for potentiometer. Do you see that little slot right in the middle? That's actually a dial you can physically turn with a screwdriver. So if the LM317T is the bouncer, restricting the electricity, the Pot5K is the club manager whispering in the bouncer's ear, telling him exactly how strict he needs to be. When you turn that dial, you change its resistance, which sends a direct signal to the LM317T to either crank up or lower the output voltage. This right here, this is what makes the whole circuit variable and totally under your control. So we've got our power rushing in, and we've got our manager dials setting the rules. But hang on a second. If you look closely at the center and the right side, you'll spot these 2 small black cylinders labeled IN4007. If our voltage is already being perfectly regulated, why on earth do we need these extra little guys bridging the wiring pathways? Well, in a word, protection. This is a brilliant example of thoughtful circuit design. Those IN4007 components are diodes, and a diode is essentially a one-way street for electricity. Think about it. Sometimes when you power off a circuit, or if something goes haywire with the device you're powering, electricity can actually try to surge backwards up the output wires. If that rogue reverse voltage smacks into our delicate LM317T chip, it's game over. It'll fry instantly. So these two diodes, they're the tough bodyguards. They guarantee electricity only ever flows downward. If a spike tries to sneak backward, the diodes just block it and safely route it away from our star chip. All right, direct your eyes down to the bottom left. See that big battery-looking cylinder labeled 470 UF50V? That's our capacitor. The thing is, electricity coming from wall adapters is rarely perfect. It can be noisy and full of little ripples. The capacitor acts just like a shock absorber or a tiny reservoir. It fills up with the incoming electricity and then releases it in this beautifully smooth, steady stream, making sure your final output doesn't flicker. And right next to it, tucked in the middle, is the R220 resistor. This little striped guy works in tandem with our POT 5K dial, setting a baseline reference voltage so our bouncer always has a stable starting point to do its math from. Let's move to how this all builds together and actually trace the chronological journey of the current. Imagine you're riding the electricity down the wires. Step 1, our chaotic 3 to 40 volts bursts in through the input DC. Step 2, as it travels, our capacitor acts as that shock-absorbing reservoir to completely smooth out any nasty ripples. Step 3, the current hits our star, the LM317T, which aggressively pinches the flow down to the exact perfect level you set with the POT 5K dial. And finally, Step 4, guarded by those one-way bodyguard diodes, the newly tamed current safely exits via the output DC, totally ready to power your gear. So, looking at the whole board one last time, it feels totally different now than it did just a few minutes ago, doesn't it? It's no longer just an intimidating, random jumble of wires and tech jargon. It's a highly logical, deeply practical system. You've got an input, a smoothing reservoir, a dial-controlled regulator, protective bodyguards, and a stable output. By breaking it down piece by piece, you've completely decoded the black box. You literally possess the blueprint now to take raw, wild electricity and master it to suit your exact needs. This one little circuit unlocks hundreds, maybe thousands of potential hobbies and inventions. So I'm going to leave you with this. Knowing that you can safely step down up to 40 volts of power into a clean, ultra-precise trickle, what DIY electronics project are you going to power up first with your brand new LM317 circuit? Let me know, and keep on learning.